Okay, in this video I'm going to continue on with exercise 7a of the book Fundamental Applied Mathematics. We're on page number 171 and the question is 10. It reads: a bullet of mass 0.1 kilograms is fired horizontally into a block of mass 2.9 kilograms, which hangs at the end of a light string of 20 meters. The bullet becomes embedded and the joint mass swings and finally comes to rest when the string makes an angle of 60 degrees with vertical. What speed did the bullet enter the block? Now, the thing about this is, if you want to use conservation of momentum, you need velocities. And what we don't have really is the velocity initially when say the combined mass moves upwards. So this, by the way, is 3 kilograms because this is the combined mass. So yeah, we don't have, we'll say, the speed it hits here. However, in previous chapters, the one on conservation of energy, we worked out how to find, if you got rid of the bullet scenario, we had kind of a pendulum, and we were able to work out the speed of the pendulum just by looking at its kinetic and gravitational potential energies and comparing them. So what I'm going to do is use, first of all, the law of conservation of energy to work out the initial velocity of the compound block here. This should actually be 3 kilograms. If it's the compound block, it's going to be 3 kilograms. Alright? And then apply the principle of conservation of momentum to the bullet. So let's just look. For that reason, I'm just going to get rid of the bullet here, right? Get rid of the bullet and make that legible. So we have a compound body of 3 kilograms because that is 0.1 kilograms and 2.9 kilograms. So the principle of conservation of energy says, if I call this scenario 1 and this scenario 2, that the kinetic energy of 1 plus the potential energy at 1 is equal to the kinetic energy at 2 plus the potential energy at 2. And this will give us the initial velocity here of the compound body, okay, which is what we want in order to use the principle of conservation of momentum with the bullet. The next thing is we need to decide our 0 point of the gravitational energy. And as I said before, you can call it anywhere. Okay, you really can decide anywhere it can be. So I suppose it'd probably be easiest if I put it here. It might even be just as easy if I put it here. But just to show that you can put it anywhere, for today I'm actually going to put it here. So I'm going to say ugrav is equal to 0. That means anything above that line is positive gravitational potential energy and anything that's below it is negative. That means the gravitational potential energies at point 2 and point 1 are both negative. So let's apply what we know. We know, of course, that kinetic energy is a half times m times v squared. So I'm going to use a different biro here. So the kinetic energy at position 1 is a half times 3 times v squared. The potential energy is going to be, I said it's negative, so it's going to be the mass, which is 3 times g times h. Now what's h? Well, the string is 20 meters, so you could say it's 20 meters excuse me, from the 0 point. And then we have the kinetic energy at point 2. Now it's after coming to rest, so the kinetic energy is a half times we'll say 3, so we know what the mass is, times 0 squared. And we have the potential energy, so it's not going to be plus, it's going to be a minus sign because, like I said, we have negative gravitational potential energy. We have the mass times g times h. Now we need to find the height at which it is. So for that reason we must use this 60 degrees. So this will give us, if we resolve this displacement vector. Okay, so we need the two vectors which when added together will create this displacement vector. So note my unit vectors here. I'm going to go parallel to the j hat and then parallel to the I hat. I'm going to put them at 90 degrees and they must be at those directions in order to add together to create this displacement vector here. So this is going to be 20 sine 60 I hat, and this is going to be, I'm going to get rid of all this because we don't need it anymore. This vector here is going to be negative 20 cos 60 j hat. Alright, now what we want is to find out the displacement vertically, because gravitational potential energy only matters in a vertical direction, or the j hat direction. So what we need to do is take 20 cos 60 from 20, because from here to here is 20 meters, and if we take, no, we don't actually even need to do that, excuse me, I take that back. We just need to find out what 20 cos 60 is. So 20 times the cosine of 60 gives an answer of 10. So what we can say here is that this this displacement is negative 10 j hat. So the height in this case is going to be 10. Alright, so let's plug all of those in. If you multiply across by 2, we get 3v squared. Okay, 3v squared minus, one sec now, we're going to have negative 120g here is equal to 0 minus 20 times 3, which is 60 again, isn't it? Yeah, 60g, like so. So we're going to get that 3v squared is equal to 60g. If we rearrange that, we're going to get v squared is equal to 20g, and v is equal to the square root of 20g. What velocity is that? That is the velocity of the compound body after the bullet has connected with it. So I'm going to rewrite that v is equal to square root of 20g. Here. Alright, so just let me clear up the diagram here and we'll get stuck into the principle of conservation of momentum. So I can get rid of essentially this part here. Right, so just to clear up the diagram and get rid of all this. Right, now the scenario we have is that there's a 3 kilogram compound mass moving after being hit by a 0.1 kilogram bullet moving in the I hat direction. So let's apply the principle of conservation of momentum. So we're going to get 0.1 times its velocity plus 3 kilograms times its velocity. So its initial velocity is 0. Obviously before the bullet hit it isn't moving. Then we get the mass of the compound body times its velocity, which is root 20g. So we're going to get v is equal to 3 over 0.1 times the square root of 20g. So bear with me one moment now and I just calculate that. So you have 3 divided by 0.1 first of all, and I need to multiply that by the square root of 20 multiplied by 9.81, giving us an answer of 420.21 meters per second. And you say to yourself, well, does that make sense? Before you even look at the answer, well, you know the speed of sound in a vacuum is about 330 meters per second. So we know, of course, that a bullet moves faster than the speed of sound. So that's, it seems in the ballpark anyway. So let's just check the answer. So on 7A question 10, and 420 is the correct answer. So thanks for watching. Please pass it on to your friends and subscribe to my channel.